We can determine if a function is continuous at a certain point if it meets these three criteria. So first, the function at that specific point, let's say our point here is a, must exist. Second, as x is approaching that a value from the left, our function must be approaching that same f of a value. And same goes for the right. As x is approaching a from the right, our function must also approach f of a. Let's look at an example of this here. So let's say we have our coordinate plane here, and we have one piece of our function is a quadratic function, and the second piece is a linear function. Now, if we were trying to figure out if this function was continuous here, let's say that this is x equals 1. Let's say this point here is where y equals 2. If we're looking at our three criteria, we are meeting those second two criteria. So as x is approaching 1 from both the left and the right, our function is approaching 2. So those second two criteria are met, but we have an open circle here at f of 1, and so f of 1 does not exist. And so therefore, this function here is not going to be continuous at x equals 1 because that point f of 1 does not exist. We did not meet all three of these criteria. We have to take a couple of additional steps to figure out if a function is continuous at a point when we are not given a graph. So I'm going to go ahead and erase this here. For this problem, we are using this piecewise function, and we want to figure out what value of k will make this function continuous. Looking at this example, we know that the first piece of our function is quadratic because it has a degree of 2. And we know that the second piece is linear. 3x minus 5 is linear. Quadratic and linear functions are always going to be continuous on their domains. So the only place we might find a discontinuity is where that first function ends and the second function begins. This occurs at x equals 2. So for every x value that is less than 2, our function is defined by this quadratic function. And for every x value that is greater than or equal to 2, our piecewise function is defined by this linear function 3x minus 5. For this function to be continuous at x equals 2, both functions, the first piece, that quadratic piece, and the second linear piece, must have the same output when we substitute in x equals 2. To figure out what value of k makes this function continuous, we want to first substitute x equals 2 into the linear function because that is the function that doesn't include our k variable. So what we are going to do is we are just going to substitute 2 in for x in that linear piece. And that gives us 3 times 2 minus 5, or 6 minus 5, which we know is equal to 1. Because 2 is included in this inequality, we have x is greater than or equal to 2. We know that our function is defined at f of 2, and when x equals 2, f of x is going to be equal to 1. For this function to be continuous, the other piece of our function, that quadratic piece, must also approach 1 from the left. So to figure out what value of k will make this function continuous, we want to set this quadratic piece, kx squared plus 3, equal to 1. So now we're going to do the same thing. We're going to substitute 2 in for x because we want to see the value of our function as it is approaching x equals 2. So we are going to substitute 2 in for x, which is going to give us 4k plus 3 equals 1, and all we have left to do is solve for k. So we're going to subtract 3 from both sides to get 4k equals negative 2, and then finally we're going to get k equals negative 2 over 4, or negative 1/2. So this tells us that if we substituted negative 1/2 into this function here, we are going to get f of x equals negative 1/2 x squared plus 3 for x is less than 2. and 3x minus 5 for x is greater than or equal to 2. And this piecewise function here is continuous at x equals 2.